wonderful title. It's one that we've actually used before, he and I, and SISE. But I thought I would make it a little bit more specific. 50 years, a lot can happen. It's going to take about 50 years for climate to play out, or even to get us on a track that we think will play out. So I decided to change it and talk about where is climate going. And you can see this is this, I'm going to change my, get a pointer here, laser pointer, right. So this is going to be the symbol of climate change. And that's an image from the book we assigned, Thinking Person's Guide to Climate Change, for one of the reading groups, which just shows where's the cooling occurring. It's obviously in the Northern Hemisphere. It's more specifically at the North Pole, but it's spread throughout across the Earth. So this is a great symbol for climate change. And here's the outline. Talk about decarbonization. So we can talk about what is it. Well, the temperature is getting warmer. World is getting warmer. As you see here, a very interesting fact. Let me make this point on this very first slide, that the cause of climate change is too much carbon emissions, right, over a period of 100 and more years into the atmosphere. And it's starting to have its effect. So while the cause is universal, doesn't matter where that carbon dioxide comes from, anywhere on the planet, it's going to have basically the same effect, because it gets mixed into the atmosphere rather quickly and affects the entire Earth. But the impacts are quite different. So you see much more warming in the north, near the North Pole, the Arctic. Plenty of stuff in the news just since beginning of this calendar year about climate change that is quite unusual. And in the West Coast, it's very different than it is, let's say, in Chicago, and that's different from Florida and so on. So the impacts are quite local. And that is a central point that I think is going to permeate this week's program. And we have to react to what happens to us locally. So although the cause is clear and we know what we have to do, decarbonize by 2050, when it comes to what do you have to do locally to get ready for it, it's going to be different. If you live on the coast, it's different than if you live in the West, than if you live in the Northwest, let's say, and the hurricane shores, so that would be the Gulf and the Atlantic, that's going to have an even different impact. So the impacts and the resilience and adaptation are quite different. So that's what we're going to talk about. So here's the outline: decarbonization, local climate projection, and then resilience and adaptation. So let's see if I can make myself, yeah. So here's a very interesting graph of the temperature, 10-year moving average, the annual and the 10-year, and you see very clearly an upward trend from 1850 to 1900. Didn't change much, went up and down some, but had about the same average. An increase from, let's call it 1910 to 1940, flattened again for until maybe, sometimes people say 1980, that's what's in the headline of this graph, and then goes up quite steadily, of course, to here only. And this is a primitive form of climate prediction. Just extrapolate that line. Don't use any models, don't do anything, just put a ruler down, draw the line, where you're going to be, and you can see what the predictions are. So it would be 2 degrees by, let's call it 2060. And 1.5, that's another milestone we hear about all the time. That would be maybe 2040. So will this simple linear extrapolation come true? Hard to know, but it's quite concerning. Let's see, can I? So you might ask, who's producing the emissions? And you see 2 graphs here: total emissions on the left, per capita emissions on the right. Let's take a look at total first. It's clearly China, although it wasn't always China. Go back before about 2005, it was the United States. And the United States has been, well, increasing, but lately actually decreasing. China has been increasing enormously. And then here's the EU, here's India, Russia, Japan, and international transport is picked out here for some reason, but you can see where these all fall. If you look per capita, it's a different story. US is by far the winner. So per person, we are producing more carbon emissions than anyone else. Russia is right up there. Japan has actually it's an advanced, developed country, yet its carbon emissions per capita are quite low. Same with the EU, and remarkably China also, although it's rising, but has not yet got, its fourth place. So, and here's the global average here. So India, well below the global average. So it's interesting. I draw no conclusion from this, many conclusions you could draw, but piece of information. This is also very interesting, that public awareness of climate change has really increased in a very positive way. So Pew Research Center every year does climate survey, same questions all the time. Here it is, here's the results from 2011 up through actually only 2020. So there should be one more year on here, which I don't have. But here's the questions. Should we develop alternative sources such as wind and solar? And here's the way the answers have varied over since 2011. And you see quite recently here, nearly 80% of these are adults say, yeah, we should develop alternative sources such as wind and solar. How about another question? Expand production of oil, gas, coal, and natural gas. Well, at one point, they were about the same. There was about as much sentiment in favor of that as renewable stuff. It's now fallen off, and it's pretty low now. So it's around 20%. And both should be given equal priority. Hardly anyone actually believes that. So very interesting. And this doesn't add much to what we're saying, but it does give the feeling that acceptance that something should be done about climate change is growing. So 61% of US adults say climate change is having at least some effect on their local community. And that's these two sectors right here. And most of these are people, as you might expect, where severe weather or rising sea level has already had effect. I'm guessing that if you ask this question now, it would be even higher. That just the last 2 years, it's become much more obvious. So 3 pillars of what we have to do. We have to decarbonize, is what I put in the outline. Biden says the grid by 2035, the economy by 2050. The grid is a little ahead of the game, but interestingly, since the new administration made that statement, others have come in to say we need to do the grid by 2040 or some other timeline which precedes the full economy, the 2050 target. We also need to project local climate change, and I put down with artificial intelligence. You'll hear about this from Rao Kodamarthi when he speaks later in the week. Why do we need to have artificial intelligence? And the answer to that was already anticipated by one of the fellows last week who said some of the climate change programs are so complicated, they take a month or even longer to run. And one of the things that artificial intelligence can do is eliminate some of that first principles calculation and in a sense, replace it with common sense. And that can dramatically speed up the climate programs, maybe by a factor of 100. And the advantage of that, if you go a factor of 100 faster, it means that you can run 100 times as many simulations at the same time period. And you can put some different assumptions in there. Well, maybe the carbon emissions profile from now until 2050 will be strong. Maybe it'll be weak. Maybe it'll have some modulation in it. And you can start to see what the effect of various assumptions would be. That is a tremendous step forward because all climate programs are really computation limited at the moment. So you want to run them faster. There's another thing you want to do, and that is to run them at higher resolution. So the resolution of many global climate programs is quite large. Hundreds of kilometers is the spatial resolution. you'd like to make that very much smaller. The size, let's say, of a city, or the size of a community, or the size of a coastal area. What you can do now is about 12 kilometers. That's really very good. It's still not good enough to include the effect of convection. So to get convection in there at a reasonable certainty, you need to be down to 4 kilometers. And if you want to have clouds simulated with, again, some reasonable certainty, you need to be down to 1 kilometer. So although we made a lot of progress on the spatial resolution, we still need to go farther. And in fact, artificial intelligence can help with that as well. So that's a second thing. We have to predict what will happen, let's say, to Chicago or Miami or Seattle or San Francisco or New York, any of those places. They'll be all different. What's going to happen so we can get ready for it? And that's the third pillar here, resilience and adaptation to climate threats. So lots of things you can do. I'll give you an example. A climate program may predict or project, I think is the right word, it may project, oh, the rainfall will increase by this amount by 2030, 2040, 2050. But that's not really quite what you want to know. What you want to know is, where's the floodplain? What's going to flood in 2040 that's not flooding now? And if we knew that, we could then get ready. So what would we do? Well, if you're talking about sea level rise, well, you might build a seawall. Talking about flooding on the Mississippi River, number of things you can do, not to say what they are. Probably building levees is not the best idea, but there are other things you can do to prepare for that. You can also ask, what would the effect be on infrastructure? And we're seeing that in the West right now, in the sense that the threat of wildfires is causing PG&E in California to turn off the power in certain areas because they don't want to take the chance of setting off a wildfire. And that means that lots of people in say in the middle of a heat wave, do not have air conditioning. So it's a complicated, as we were saying earlier, set of possibly cascading disasters that you have to get ready for, and knowing with some certainty how hot will it be, how much rain will fall, and other things, what will the wind be. That's very important to get ready. So these are the three things that really we have to do. How do you do it? Well, okay, we need to decarbonize the economy by 2050. This report came out in May of this year by IEA, International Energy Association. Highly respected. Everybody was waiting for this report. It's the first time, well, what do you see here? You see the carbon emissions from the various sectors: buildings, transport, industry, electricity and heat, other. You can see over here at 2020, how big is this for each one of the sectors? Obviously, electricity and heat is pretty big. Industry and transport. Buildings, not the biggest one, but very significant, and that source has to be eliminated along with all the others. And what they did was project out to 2050, how could you possibly get to zero? This is for the world, not for the US or for any particular country. It's the first time it's been done for the world. And you basically work backwards, right, from this 2050 goal. Where do you have to be in 2040? Where do you have to be in 2030? It looks pretty simple when you look at it this way, but it actually is very aggressive. And here are some milestones. So by 2030, for example, we have to be adding solar and wind generation to the grid at 4 times the rate in 2020. And I can tell you, you know this, that the rate in 2020 was already a record breaker. That was the most we'd ever put in any time. We need to do it 4 times that rate every year, and we have to keep that up from 2030 to 2050. That is very, very aggressive. Here's another one at 2030. All new buildings are zero carbon ready. So that means, and Berkeley, I think, was the first city to legislate that beyond a certain date, I think it was 2035, but beyond a certain date, no buildings will be allowed to be built with gas infrastructure. They have to be completely electric. There have been some other cities and even states since then that have followed suit, and also quite a reaction to that, as you might expect, saying that that's impossible, and uh, that reaction is certainly very favorable to the natural gas industry. So here's 2035, 100% of personal car sales have to be electric, and 50% of truck sales have to be electric. That's an aggressive goal. 2040, net zero electricity grids globally. So this is not 2035, it's not 2050, but it's in between. And remarkably, we get to 2050, we still will not have gotten rid of all the CO2, at least in this scenario. We will have captured by that time 7.6 gigatons of CO2, and that's about 25% of the 2020 output. So this is, as I say, has had quite an impact because it's the first time that it's been done. It has some respect for its accuracy and for its care, and it really is. It's really an aggressive target. So what does that mean? Can we do this? And this came up in our reading group. Do we have the technology to decarbonize by 2050? And I think there's several ways to characterize that answer. You may say, yes, we have all the ideas we need. We just need to put them into practice. And that would be more or less correct. Or you could say, no, we don't have the commercial technology yet. And the key word is commercial. We have technology in the lab that we could think about deploying, but would we actually be able to deploy it? That's a really good question. So here's some conventional wisdom. You want to electrify buildings, get rid of natural gas, do everything with electricity. Yeah, you could do that. You got to have personal cars electrified. Well, we're on the route for that. Looks like we could possibly do that with the lithium-ion batteries we have now and the technology and so on. And so here the commercial technology mostly exists, and we expect that it will be cost effective. So it's not yet, but we expect that it will be. Different story when you start to look at heavy duty industry and transportation. Look at, so that means trucks and marine shipping, airplanes. Look at agriculture, land use and forestry. Commercial technology does not exist, has to be innovated. May exist in the laboratory, may exist as a concept, but it needs to be proven out, and the cost has to be brought down to the point where it can be, where it's affordable. How would you do that? Well, you're gonna have to look at advanced batteries beyond lithium ion. You're gonna have to look at hydrogen electrolyzers. That means green hydrogen from electrolyzing water, no CO2 associated with that, and direct air capture. Things that we have thought about, but are really not quite ready yet. So this is kind of the outlook. And interestingly, we talked about decarbonizing the electricity grid. Here's what you need. Of course, wind and solar generation. You need, supposed to say here, transmission. Sorry, something happened to the last few letters. And you need battery storage. So this is the way we're doing it now. And remarkably, the prices of all of these things have fallen dramatically. So this graph came out about 2 years ago from Bloomberg, and they just tracked the levelized cost of electricity, dollars per megawatt hour, 2018 dollars, and from 2009 till this came out in 2019. So you see solar has fallen dramatically. And I think everyone knew that. This captures it quantitatively. Interesting. Not quite a factor of 10, but getting close. Here's wind, offshore wind, onshore wind. Offshore, well, both have fallen dramatically. That's great. What was surprising was the cost of battery storage had fallen even more quickly than these two. So I think solar was accepted as the sort of poster child of falling prices. For batteries, it's almost a factor of 10 as well, and falling even more steeply. So a couple of lessons you can take from this. You could say, how do these prices compare with the alternative? Well, here's a gas peaker plant. That's a gas turbine that you turn on when you have to meet peak demand, but otherwise it's off. And you see that it's fallen, not as far or as fast as solar or batteries. And you might expect that. It's a mature technology. So it's already gotten all of the things, or many of the things, the learning curve has already happened for that. But if you take a look at the relative cost of a gas peaker plant for electricity and a battery, you see they're not that different. And if you just extrapolate this line a little bit and that line a little bit, it's clear that soon the battery will be cheaper than the gas peaker plant. So that kind of takes away one of the biggest barriers to full deployment is cost. Remarkably, if you look at a combined cycle gas turbine, though that's what you have on 24/7, it's base load electricity. Well, here's the cost of that. It's lower than a gas peaker plant, as you might expect, but it also is competing with wind and solar. And again, simply extrapolate this curve. The wind and solar, a few years from now, will clearly be lower than the cost of a gas combined cycle gas plant. So on the generation side, we're getting there economically. And I think that's very good news. Also, I think if you go back 10 years, nobody would have predicted that these curves would fall so fast. The battery curve was always thought to be expensive, and truth be told, it's still about 4 times as expensive as solar or wind per kilowatt hour to get electricity from a battery. So we got a ways to go there, but both getting very, very competitive. There's a problem, and this is important for decarbonizing the grid. A lithium-ion battery can discharge for about 4 hours. That's it. You could buy 2 of them, you get 8 hours, but you've just doubled the cost of that battery backup. And that's great for extending solar past sunset, let's say a few hours. That's peak demand time, so that's good. But it will not work for consecutive cloudy days or consecutive calm days. Go back in history, you can get 10 of those in a row. So to meet that standard, you have to have 10 something that can discharge 10 days with no wind and no solar. And that's a big problem. So it's called long duration discharge storage. Everybody recognizes that, and that's the big problem in decarbonizing the grid. Today, of course, you use gas peaker plants, just turn them on, they can run as long as you want, but the emissions are what you want to get rid of. And this is really an interesting problem. You could use chemical storage, such as hydrogen, and indeed you can burn hydrogen in a gas turbine with a few tweaks. And hydrogen is getting a great deal of attention now as really a ripe opportunity. So here's a little bit more about hydrogen. You can produce hydrogen by conventional steam reforming. That's over here. You take methane, water, a lot of heat, a lot of pressure, and you get hydrogen plus carbon dioxide, chemical reaction. Combine that carbon monoxide, I said carbon dioxide, it's carbon monoxide and water, and you can then get carbon dioxide and more hydrogen. This produce hydrogen this way, it produces as much carbon dioxide as if you had simply burned the methane. So it's how we get 90% of our hydrogen nowadays, but it's certainly not carbon dioxide free. The alternative is water electrolysis. And remarkably, it's much more efficient. You just take water, you put 1.23 volts, in practice it's a little higher, maybe 1.4 volts, across that water, and it splits into hydrogen at one electrode and oxygen at the other. No pressure, no high temperature. The trouble is the cost is a factor of 4 higher than this more mature technology. So you might ask the question, if we started to deploy water electrolysis, at scale, would after 10 years the price come down simply by the demand curve and the learning curve by this factor of 4? The expectation is yes, it would. So this is a very interesting opportunity. I mentioned that you can burn hydrogen in gas turbines. You have to tweak the turbine a little bit, but it's basically a drop-in replacement for natural gas. That is very, very attractive. The other way to produce, to turn hydrogen into electricity is with, it's called a fuel cell. It looks like a battery, but you put hydrogen in one side, oxygen in the other side. You basically reverse this electrolysis reaction. You get water as the output, and you also produce electricity. So this is also, let's say, a somewhat mature technology. So this is interesting. Why would you want to, or what could you do? Let's say that you did make hydrogen by water electrolysis. It was cheap enough. What would you do with that? Well, here you see the grid production, as I've shown here with wind and solar. It's all renewable. You could store that electricity in a battery. You could send that electricity cross country, hundreds or thousands of miles with transmission lines. And you would then have a distribution grid, which is homes, offices, buildings, factories, that you could power with that electricity. That's what we do now. And now you might ask, well, if we want to go to full wind and solar, it's pretty intermittent. We haven't really solved the long duration storage problem. We'd probably overbuild this because it's cheaper than building storage by a factor of 4. It's also cheaper than building a transmission line. So you would probably overbuild this and curtail it part of the time. But you could take that renewable electricity, produce green hydrogen by water electrolysis. It's very easy to store that. You just put it in a tank or put it underground, a lot cheaper than a battery. It's pretty easy to transmit it in a pipeline. Could not be the natural gas pipeline because hydrogen embrittles those steels. You'd have to build new pipelines, but still cheaper than a transmission line. You could then use a fuel cell or combustion to turn that hydrogen into electricity for the distribution grid. And on top of it, you would have a combustible fuel, hydrogen, that you could substitute for things like gasoline or diesel in trucks, heavy duty trucks. You could burn it to power marine ships. You could burn it for aviation, and you could burn it for heavy industry. So on top of making the electricity grid more flexible, you would be able to decarbonize some industries that are very hard to decarbonize now. So this is getting a lot of attention. Here's the takeaway. A single integrated, highly flexible energy system, multiple options for achieving our goals, zero emissions, low costs, high reliability, and fast recovery if something goes wrong. So think about this system. That's in contrast to the system we have now, which is pretty much composed of three energy carriers. Electricity does a whole lot of stuff, really versatile, wonderful carrier. Oil, which is pretty much for transportation. That's how we drive trucks, cars, ships, and airplanes. And coal and gas, which is pretty much for industry. Iron, steel, aluminum, cement, glass, plastics, all these things are made by burning fossil fuels to get high temperature heat. And also in all of our buildings, most of our buildings, space heating, water heating, cooking, and so on, that's natural gas. But the point of this graph is that these three energy carriers don't interact. So you're driving cars with oil and gasoline, it's heavy industry and buildings with coal and gas, and it's electricity, and they're pretty much separate. So let's take a look at some other decarbonization opportunities. We're looking at the emissions. So this also is from the International Energy Agency. The emissions of carbon dioxide in transportation. And you see it's passenger cars, medium and heavy trucks. Here's shipping, here's aviation, and here's some other things which are much lower. They're listed over here. And these vertical lines are, at least in this scenario, when you might be able to decarbonize them completely. This scenario, and it's a prediction of the future, or at least a proposed pathway, goes out to 2070, not 2050. So we have not decarbonized in this scenario by 2050. But it shows what you have to do. And it shows this big drop here in 2020. That's the pandemic. So we all use transportation much less in 2020. And that's what this is depicting. So here's the at least one sense of how you might decarbonize. Oh, and I should say, the biggest fraction is passenger cars. So we're right to have electric vehicles as passenger cars as our first target. That has the biggest impact. It's not clear that you can use the lithium-ion batteries we have now for heavy-duty trucks, for shipping, or for aviation, although some of those things you can, maybe on short distance, you can use lithium-ion, but we need something else. And I've listed the things here. So light vehicles, it's pretty clear it's going to be lithium-ion batteries. For buses, yeah, it could be lithium-ion batteries because they can recharge in their bus routes. It's around town, urban bus lines. They can recharge on their rounds, and you don't have to have a very big battery. You could also have hydrogen fuel cells, and there are hydrogen fuel cell buses out there already. For medium and heavy duty freight trucks, again, depends, is it long distance or regional? You could do battery. Tesla says yes, battery. Nikola says no, hydrogen fuel cells are better, and probably it will be a mix of those two. For rail, it's already electric, but the electricity is produced by a diesel engine in the locomotive, so we need to make that renewable. It could be a hydrogen fuel cell. Or you could simply, it's listed here, it says catenary wire, could be just a transmission line running next to the track. And you would have renewable generation of electricity that you wired into the train continuously. Marine shipping batteries probably are not the right answer. They're too big and heavy, take up space that could be used for cargo. But hydrogen fuel cell or hydrogen combustion are things being considered. You may know that Bill Gates has commissioned a hydrogen yacht for his personal use that could go across the Atlantic on one refueling. So there's an example of hydrogen combustion for marine shipping. And aviation, actually for short, regional, up to maybe 500 miles, batteries could be an option. For longer, transcontinental or international, it probably needs to be a fuel of some kind, and hydrogen is being discussed. So are biofuels and some other carbon-free fuels, but or maybe a hybrid, a battery combustion hybrid. So these are things that we're thinking about and need to do. This is heavy industry, and this is a tough one. So let's look over here first. Why is it so hard to decarbonize heavy industry? Well, heavy industry, it means you're making, let's say, cement, you're making steel, you're making glass, you're making ammonia, and you're making ethylene for the plastics industry. These are the four biggest products that produce the most CO2. How do you do that? Well, you need a lot of high temperature heat. And this graph shows, here's the temperature, and here are some of the things you need. Indirect cement, you need very high. So 1800 degrees, here's glass, here's cement at a lower temperature. Steel, it's about 1200 degrees, and so on. Lots of high temperature heat. The easiest way to get that is by burning a fuel. And until now, the fuel was fossil fuel, cheap, abundant. We didn't take climate change into account until recently, so it was an obvious solution. Now we're looking for alternatives. So that's one source of the CO2. The second source of the CO2 is from the feedstocks that are processed by that high temperature heat. So if it's iron and steel, you've got to take iron oxide. Usually you combine it with carbon to get iron itself, get rid of the oxide, and you produce CO2, that's iron and steel. For cement, it's calcium carbonate. You need to calcine that, as they say, to get calcium oxide, and you're producing CO2 as a byproduct. So it's part of the process. You have to get rid of that. So that's why it's so hard to decarbonize. And you might say over here, interesting part of this graph, what are some other fuels besides fossil fuels? Well, it could be biodiesel, could be wood chips, could be resistive heating or microwave heating, so basically electricity, could be hydrogen, could be nuclear, so advanced nuclear or what we have now, and the temperatures you can achieve. So nuclear is good for some things, but actually not most of them. Hydrogen would be a great substitute. You can do everything you want. You can do some things with resistive, you can do some things with wood chips and biodiesel. But none of them are really ideal. So we're looking for an alternative source of heat. And we're also looking for a way to decarbonize this process. And the feeling is that's pretty hard. So what people are saying now, and that's shown in this graph, we're going to have to carbon capture, continue using the feedstock, even if we get an alternative source of heat, continue using the feedstock, and at least in this projection, it's a scenario of the future, it goes all the way out to 2100, and we're still capturing the carbon at 2100. It's that difficult of a problem. So that's why this is so hard to decarbonize. Let's look a little beyond the decarbonization now. How about climate already changing? Well, here's a graph from NOAA. It lists the billion-dollar weather and climate events from 1980 to 2020. So in 1980, the bars are the number. There were 3. And these, by the way, CPI adjusted, so there's no inflation in this graph. And in 2020, there were 22. What a change. It's definitely growing. And that's the effect of climate change. You can see all the various things here that are into this graph. But they're also kind of shown here. 2020 was a banner year, 262 deaths. And here's what they were. So wildfires in the West, drought in the Midwest, tornadoes, hurricanes. We had almost 2 hurricanes in the Gulf Coast at once. One of them turned out to only be a tropical storm, so it didn't quite happen, but that's the first time we've ever come that close. Lots of different weather events. In 2021, southern freeze in Texas in February. This is an old number now, it's up around 200 deaths and very, very expensive. Basically, that should never have happened. We could have been ready for that, but we weren't. So the point of this graph, climate change is already here. We need to prepare for it. It's not something we can wait until 2020 and say, oh, good, we decarbonized. Nope, we've already got it. So what do you do? Well, you want to model local climate with artificial intelligence, as I was saying. You'll hear more about this from Rao later in the week. And you want to get 12 kilometer, maybe 4 kilometer, maybe 1 kilometer resolution. So you can see where the floodplains will be. You can see what the wind damage might be. You can see how bad the droughts will be. So high winds and drought and high temperatures, they all go together. Recently, Argonne had a contract with AT&T to look at climate change in the 4 southeastern states, Florida, North Carolina, South Carolina, and Georgia, and what effect it would have by 2050 on AT&T's communications infrastructure. That's their cell towers, that's their underground fiber. So that we need much more of that. And the second thing, besides climate prediction, is resilience and adaptation. What will the effect be on floods so that we can get ready for it? That's very much a local issue. You'll hear more about that from Tom Wall, who will talk later this week on some of the things that have already taken place. But this is becoming a much bigger problem. That's it for me. Love to have some questions. And I cannot actually see the chat. unfortunately. So,
That's okay, George. I will help you.
okay, thank you, thank you, thank you. Let me turn off my slides.
Fantastic. So I've been behind the scenes for everybody who's been watching SISE at home. If you're an alumni, you know who I am. My name is Thomas. I'm the program coordinator, and I tend to just kind of be invisible. But today I get to play moderator. So with that, I'm really excited to have some of our fellows ask some questions, and I'd love to start off with Noah. If you could ask your question that was referencing something much earlier in George's presentation.
Sure, Thomas, and thanks, George, for a great presentation. My question is regarding that first IEA figure with
Right.
the targets. I was just wondering, which of those do you think presents the greatest challenge?
Ha! It's a great question. They're all challenging. But I will tell you, let's see if I can pull that one back up. I probably can. Yeah. Yeah, they're all challenging. But as we said, the grid is probably the easiest one, simply because, I'll leave this on, simply because we're already deploying wind and solar. And if we have to deploy it at a huge rate, that's a practical deployment question. But maybe we might be able to do that. We haven't solved the long duration discharge storage problem. Right now it's natural gas. Maybe it could be hydrogen. Maybe we could have a battery that has, say, 5, 6, even a 10-day discharge time. That remains to be innovated. But other than that, we're well on the way. Probably going to get the personal cars done because, again, it's just a matter of rolling it out. These others are tougher. To me, the toughest one is heavy industry. I don't see how to do that. The industries are all a little bit different. You do a different thing for cement than you do for steel, than you do for ammonia. So you can't have one solution that applies to all of them. So we have to take those in sequence. And I think agriculture is a pretty tough one. It's usually not discussed in the context of energy, that its emissions are often put off on the side. We really don't know how to do that yet. And it will be a different set of solutions. You can't just think of electrifying agriculture. I mean, you could electrify this big machine here, but the other things about agriculture, you can't. So I think the grid's easy. I'm going to say easy, quote unquote. Industry is a tough one. We'll probably get the shipping and the heavy duty transportation, including airplanes, done before we get manufacturing and agriculture done. That would be my guess.
Great, thanks, George. I'm going to ask two fellows to ask their questions, one right after the other, Shashwat and then Adele, because they both deal with commercializing technology. So Shashwat and then Adele, and then George, if you can respond to both.
Sure.
Yeah, I was wondering, how long does it typically take to commercialize a technology that has been developed in the lab?
Yeah, that is a terrific question. And you can look at solar cells, would be a good example. In fact, we had this here somewhere. Let's see. Yeah, here it is. 10 years to actually deploy. So we're nowhere near 100% on, where we need to be on solar cells. But after 10 years, we made a big dent. I don't, and if you want to, where would you start? It's probably 5 years after you do something in the lab before you can scale it up to deployment scale, commercial scale. And then you start deploying it, it might be another 10 years after that. So there's a huge time lag here. And I think we have to take that into account.
Great. And how about Adele?
Yeah, and I also had a question. So there's the issue of commercializing tech, but then there's also the issue of getting policy passed. So I was curious Like, how are we going to be able to speed up this legislative process in order to get the widespread adoption of these new technologies once they come out?
Great question. And I think the two things you mentioned, these two questions, you got to scale up. That's kind of a technology problem, but you also have to have policy. And you really can't go anywhere without policy. I will say that it was Japan and Germany who, way back here in 2010, had feed-in tariffs for solar in their countries that encouraged the deployment of solar. And that encouraging the deployment, that is increasing demand, is what helped the economies of scale and the learning curve to lower the cost. So they do go hand in hand. My view is that we need to leverage this learning curve, make it happen again for green hydrogen from water electrolysis, and for other things, because it's a huge asset. Let me go off on a little bit of a tangent here. We talk about energy justice, climate justice, environmental justice. A lot of that has to do with the cost. So if things are expensive, the underserved and marginal communities can't afford them and they don't do it. So if you're going to have all three kinds of justice, energy, environmental, and climate, you got to get the cost down. So I think getting the cost down is not just a capitalistic challenge or a goal or, let's say, a target. It's also a justice target. You really do have to get the cost down. So policy plays a big role there. And there are other kinds of policy that we need to put into place as well. I think California is one of the states that understands this and has been doing it for 20 years. And we could all take a look at California as a model for how do you go forward. It's pretty clear the Biden administration wants to do it too. They have big visions and big plans. And they just announced, for example, I don't know, 2 or 3 weeks ago, a goal of getting the price of green hydrogen down to $1 a kilogram, which would be completely competitive with hydrogen from methane, steam reforming. And so they got that goal. They haven't put policy in place yet, but I'm guessing that they will. It's an enormous tool.
Fantastic. Thanks, George. So 2 more fellows have related questions. First, Rebecca, and then Gracie, and this has to do with developing countries.
Yeah, thank you, Thomas. Thank you for the presentation, George. So my question is more about the climate models that you were talking about at the beginning. So these high resolution models, especially if we actually include machine learning, artificial intelligence, will require big data. Will require huge data sets that like high resolution historical data. And is there a concern that we won't be able to predict extreme like climate events in developing countries where this data is not that available, and so they are going to be, and they are even more vulnerable to these climate events? So that could be a weakness of these climate models, maybe.
Yeah, great point. So the whole question of artificial intelligence very much in the news now, everywhere. And in climate, it's interesting how it's applied in climate. So what they do with climate, and again, you'll hear more about this from Rao later on, but they take a very carefully done simulation, climate projection for the future that takes months to run on a computer. And they take that as their training set. And they use that training set to kind of fill in the blanks. So you may be familiar with, I've forgotten the exact word, but you make an image more perfect than it was. Because if you have a face, for example, 1 million pictures of faces, there are certain characteristics of every face that you can extract from analyzing a data set of 1 million pictures of images of faces. Then you can take a particular face, and let's say the pixel density is not high enough, doesn't have very high resolution. You can use the information from the million faces that you've already categorized at high resolution to actually increase the resolution of that image of the face. It works remarkably well. Been working on this for a decade, so it's not surprising that it's made a lot of progress. Well, you can do the same thing with the very high resolution, carefully run climate scenarios to get higher spatial resolution. So you have that high spatial resolution in lots, let's say, thousands of examples. You extract the common features from that, and you apply that learning to, let's say, a low resolution or a low resolution projection for a developing country, let's say, and actually emulate, is the word they use, the high resolution results. So long story, bottom line is that it's possible to get high resolution results using artificial intelligence from lower resolution projections. Admittedly, the actual data is not there from the developing countries, but we can still make projections that, let's say, are approximations to what will happen. So my own view, to answer your question directly, it would be possible in a few years to have the projections needed for developing countries to make all the preparations that one could make in a developed country. And the fact that the raw data in terms of measurements wasn't there can be accounted for. So it won't be perfect, but it can get you a long way.
Great, and thank you. Gracie, how about you?
Yes, my question is, what's it going to look like for decarbonizing impoverished or developing countries, since they don't already have high industry or stable grids? What kind of support do they need to create a grid that is decarbonized without going through the phase of an unclean grid per se?
Yeah, great question. And of course, with developing countries, they are allowed to skip some of the steps. The developed world went through a fossil grid, 100% fossil grid. Developing world doesn't have to do that. So you're going to build a grid with wind and solar immediately. And you see from the graph of the costs, it actually will be the cheaper option going forward. So there's some advantage to delaying building the grid. You can start from a much higher level. There will be a question of resources. So, I mean, when you're going from a very primitive grid to, and you have in mind your target as an advanced grid, like the ones, let's say, in the developed countries, takes a lot of capital to do that. Where will they get that? Very good question. I think that's unresolved. There is a feeling or a movement that the developed countries should donate $1 trillion or some big number to the developing world in order to provide the decarbonized grids and transportation. Why should the developed world do this? Because it cuts down the carbon emissions and helps the developed world. So there can be, let's say, a selfish or a self-interest reason for wanting to do that. That idea has not taken off yet. It's been suggested, hasn't taken off yet. But my feeling, as climate change gets worse, the weather gets worse, and we all feel that it's more urgent, that idea may take on a little bit more of acceptability.
Great. And let's hear from Sebastian, please.
All right, so I was wondering, this was also for the same graph that Noah had a question about. And it was, do you think we can do anything to increase the carbon capture total? And I also had a question about the 7.6 gigatons of CO2. Is that like collected per year by the time we reach 2050, or is that all we've collected from now?
Yeah, to answer the second one first, I was confused by that as well in that report. That is what you have collected by 2050. So you're starting to collect as soon as you can learn how to collect. And by 2050, you would have collected that amount. and presumably continue to collect until you can figure out how to just eliminate the fossil fuels altogether. Your first question, do you want to clarify that question a little bit? Your first question?
I guess, is there like any initiatives for carbon capture aside from like CarbFix that like you see with any promise between now and 2050?
So I think it's an unknown. There are lots of ways, there are ways to capture carbon. You can do it chemically with amines. And that's been around for a while, actually works. Mostly that's been thought of as capturing carbon from the flue of a chimney, power plant or something. Capturing it directly from the air is much diluter, it's a much tougher problem. But the amazing thing to me is that in the last even 2 years, people have said, we have to learn how to capture the carbon. We've gotten serious about the 2050 deadline. We can't go beyond that because the consequences are so bad. We're not going to be able to eliminate the emissions, so we're going to have to learn how to capture. And I think that willingness is much stronger now than it was even 2 years ago. So I think that's an innovation challenge. And I'm no expert on that. I can't tell you what the latest ideas are, but it would be very interesting to look into that.
George, so coming from YouTube, Nadine, who's one of our 2013 alumni, shot us a note which relates to Sebastian's, and she says, are carbon offsets a feasible alternative for situations where we can't be completely net zero? And she gives an example, and I think she's speaking from kind of more personal rather than like institutional, but maybe you could address both. She says, for example, could you plant X number of trees to offset the CO2 emitted for gas use? And maybe we think about that, like if we're using gas at home on our stove, is it okay to just go out and plant 2 trees and call it a day, or like even up to like an institutional level as well?
Yeah, great question. So carbon offsets in principle work. I think it's a question of time scale. So if you're trying to offset carbon emissions that happen today and you said, I'll plant 2 trees, it's going to take a while to get those trees in the ground. They're going to have to grow. They're not going to reach their full potential for 10 years, let's say 20. So there is a time offset. And I think it's a little risky to think that that did solve the problem. You have to kind of monitor it. And if it's not solving the problem, you have to take something else into account. So I love the phrase you used, Thomas, saying plant a couple of trees and call it a day. It isn't that simple. You really have to watch what you're doing. It is a powerful technique, and the ecosystem, natural ecosystems around the world, I'm thinking of the Amazon forest, but many more, could do a lot to absorb that carbon. But we need to understand that process, and I think not dismiss it lightly. It's still a challenge, and it has to be done, of course, on a huge scale. Beyond that, I think another even better answer is we shouldn't rely on offsets. It would be better to eliminate the emissions. And if we can make that solution work, that's where we ought to have our target.
Great. And I'm going to ask Dravika and Sam to go right after each other. Dravika, you're asking about environmental impacts and extraction. And Sam, you're asking about once-through economy for recycling. So let's start with Dravika.
Yeah, so am I audible enough?
Yes.
Okay, cool. So here goes my question. Considering the fact that renewable energy itself also has a plethora of environmental impacts, such as unsustainable resource extraction, especially through deep sea mining in order to supply materials for solar or EVs, and also the harm caused to wildlife by windmills. So is there a system to assess and monitor these impacts and develop redesign strategies? And if there isn't, do you think it is wise to aim at full replacement without an adequate impact assessment or a maximum risk alleviation strategy?
Yeah, great question. I think we're becoming more aware that there are impacts, say upstream or downstream, from many of the renewable technologies, supposedly renewable technologies. Mining is a very good one. And Lithium-ion batteries are a great example. Very complex supply chain. Takes cobalt, takes nickel, takes lots of other, takes lithium, obviously, but lots of other minerals. And mining is notoriously not very clean. You're out somewhere in the, in the desert or the wilderness, and you need machinery. The way to get machinery is with diesel power. And that's the way a lot of mining is done. So that footprint has to be taken into account. We shouldn't be overconfident that we can actually solve that problem. I think I'll give you the example again, lithium-ion batteries. Until recently, all the gigafactories operated on fossil power. So they maybe took some electricity from the grid, but of course a lot of that was fossil electricity. Or you simply burn fossil fuels to make the batteries. That's a huge carbon impact. What is happening now, and I think Europe is taking the lead, there's a gigafactory in Sweden called Northvolt, which is supposed to start operating within the next 2 years, that is run completely on hydropower. And it's in the northern part of Sweden, there's plenty of hydropower. So that dramatically reduces the carbon footprint of battery manufacturing. Doesn't take it to zero. And of course, there are other parts of the battery assembly process that still produce carbon dioxide. But it's a big step forward. And we need to look at things like that all along the supply chain. So I think you're right on target. Are we making progress on that? Maybe it's a little slower. We're thinking of the major impacts that we can start with first, and we'll come around and pick up some of these smaller impacts later, but it's absolutely essential to do it.
All right, and we'll take one more question from Chaitanya.
Definitely, thank you. Hi, George. My question is more around the up and coming trend with SMR hydrogen with CCS, which is being labeled as blue hydrogen. So from what I've read and I've seen in the industry, it seems a lot of the current refineries are shifting from their 90% gray hydrogen mix towards CCS hydrogen instead of directly making the move to green hydrogen. So I was just wondering, like, what are the potential issues with CCS? Because from what I could see with where they store it, the carbon is still there. It's managed in a temporary way. It's not gone, right? So I was wondering, like, if this is like a ticking time bomb, or what's the deal with CCS?
Yeah, it could be a ticking time bomb. There's several options. Great question. First option, you capture it and you store it. So there's several ways to store it. You could store it underground and just let it sit there and hope it never leaks out. And you probably could achieve that. There's a better way, though, to store it. And that's to store it with some silicates, let's say, because carbon dioxide reacts with almost nothing because it's already in such a low energy state. But it does react with silicates to produce carbonate. So instead of CO2, it's CO3. Could be sodium carbonate, could be calcium carbonate. But that's even more stable than carbon dioxide. So if you can induce this chemical reaction naturally with silicates that you've dug up from the ground, they're pretty easy to come by. It's not a hard process. And you promote that reaction, you're storing it in a way that's really permanent. It doesn't leak out. It's already been converted into something that will stay there forever. Most rocks are carbonates, and the rocks have been around for 60 million years. They're not going anywhere. So it's a really good way to store the carbon. Another thing you hear about a lot is let's utilize the captured carbon, turn it into something useful. And here it's really not quite as good for being net zero. So you've turned it into a useful product that, say you've turned it into ethylene and you've made plastics out of it. But those plastics still have the carbon embedded in it. They're still out in the environment. They're not sequestered away. And they are eventually going to release that carbon. So it's not as good a solution. And the best it can be is carbon neutral, you could never make it carbon negative because you haven't put the carbon away for good. So I think there's a lot to do here. There's a lot of knowledge we don't have. There's a lot of ideas that we have not explored, and it's early stage.
All right, fantastic. So we'll call the session there. Thank you so much, George, for the wonderful presentation and for taking all the great questions by all the fellows, hard-hitting as they were. We'll be back in about 20 minutes for another panel, which George will kick off, talking about innovation and specifically responsible innovation.